Hello there and welcome to this presentation on the fundamentals of chip-to-cloud IoT security. My name is Chris Jones. I'm the Senior Security Specialist at Quantique. So let's have a look at what we're going to cover in the presentation. So first of all, we're just going to show you what we mean by a chip-to-cloud IoT network, and then we're going to talk about device identity and how important it is for a connected device. Then we're going to talk about roots of trust and how these roots of trust can be created in silicon chips. And then we're going to look at the different root of trust technologies that are out there and compare them for you. So let's have a look at the IoT network. So as I'm sure you're aware, there are billions of devices that are deployed every year, and they include some intelligence, basically either a microcontroller, system on chip, or some other device inside a connected product. Each of these edge devices, we could call them, are where there's a potential for a hacker to gain access to the network. Most of the connected devices, what they do when they're connected, actually talk to applications and services that run on either the cloud or on-premises servers. Some examples of cloud services are AWS, Azure, Mosquito, Google.com, etc. So let's have a look at a simplified IoT network. So here you can see, we could call this a connected product, and inside it will have some kind of intelligence, as I mentioned before. So we're talking about microcontrollers, system on chips, microprocessor, and this is what runs your program. It generally gets connected to some kind of sensor in order to pick out information about its environments, things like temperature, humidity, things like that. So basically these two together can form some kind of connected product that allows it to send data to a network over some kind of link. So as it says here, the chip security underpins the device security. So the security in this microcontroller is what underpins that device security. And the way you start by giving this device security is by giving it a unique identity. So basically this product in the purple here has to have a unique identity. This is one of the fundamental keys of security. Then we have this link. So this is the link between the device or product and the cloud. This link really needs to be an encrypted link, and this is where you can send your data over this secure link. The encryption of the data over this link is done using cryptographic keys, and those keys tend to be derived from random numbers, or what we call seeds. And there are various things inside the device, microcontroller or other device, as to what uses to generate those random seeds. What you do with those seeds is then generate cryptographic keys, which can be used to prove the identity of the device. Then over here you can see the cloud hosted applications, and these are the applications that extract the data from the encrypted link and then process it to do whatever function the end customer wants to do with that data. As I described in the previous slide, to have security in your connected device, there's two fundamental things you need: a unique identity and some cryptographic keys. And it is those two entities that provide you with a root of trust. And the fundamental function of the root of trust is to provide unique identity and then to be able to prove that identity. And the proof is done through cryptographic keys. Now let's have a look at how a root of trust is actually put into an IoT device. So there are two methodologies shown here. One is by using an external computer called a hardware security module. This is basically a computer that's dedicated to generating random numbers and cryptographic keys, and also managing those keys. These keys typically are generated externally, and they're programmed into the intelligent device, i.e. the microcontroller or the system on chip. The injection is done over some kind of programming interface. And typically there are some issues with security here, as that interface can oftentimes not be encrypted. The other methodology is whereby the chip itself can actually generate the unique values and convert those into cryptographic keys. Typically the semiconductor device may use some random physical variations that's actually inherent in the semiconductor process and use those to generate random seeds. These are typically called physical unclonable functions, or PUFs. These puffs generate these random seeds, which then can be converted into cryptographic keys by some kind of key generation accelerator, often a peripheral already integrated into the semiconductor device. Let's have a look at the key injection method and some of the security compromises that you have to make. So typically it's a little bit more expensive. The reason for that is that you need specialist programming equipment. Usually that's provided by a specialist programming house, and they provide programmers that are linked closely with HSMs. Because you're dealing with a third party, that also is a security risk. The keys tend to need to be stored in some kind of memory inside the device. They're generally put in some flash and then protected by some hardware security technology inside the semiconductor device. Typical example of that is trust zone. Those keys can be vulnerable to leakage and side channel attacks because they're just sitting in standard flash memory in the device. The keys are then often transferred to devices over an unencrypted link, so that's between the HSM and the programmer, which can expose the keys to attackers. Let's have a look at these physical unclonable functions in a little bit more detail. The first one we're going to look at is the SRAM PUF. How does this actually work? Well, the SRAM PUF takes advantage of SRAM that is generally embedded in most microcontroller or microprocessor devices. When you actually power up these devices, the actual ones and zeros in the SRAM can be quite random because it's dependent in tiny physical variations of the silicon wafer. And it is these variations that are random in nature that is used to create the seeds that can be used to generate cryptographic keys. Basically, the SRAM in a device can become the fingerprint of that device and provide the device with a unique identity. SRAM puffs are really cool in that they're actually using a technology, i.e. SRAM, that is already in a microcontroller. The only additions that you need to take full advantage of it to make a puff is of course some software to drive the actual puff itself. Let's now have a look at the pros and cons of these puff technologies. Let's first have a look at the SRAM variant. So benefits of this are of course that you don't actually have to inject keys into the device. The seeds to generate keys are created by the SRAM itself, which is already in the device. The actual identity itself is not stored in memory as such, i.e. it's not stored in some flash memory which could easily be extracted. It's actually stored in the physical makeup of the SRAM cells, so it is quite difficult to hack. SRAM is already present in most MCUs, so the peripheral is already there and you're going to take advantage of it. And it's available by different vendors. Some examples here, Microsemi, NXP, etc. They can provide software to create SRAM puffs. Some of the limitations, however, are that this generally tends to be only one seed, and if you want multiple cryptographic keys you have to generate it from this common seed, which means that they can be mathematically correlated. Cells don't always start up in the same preferred state. This means that you need some kind of helper data or additional information to make sure that the actual key that you're going to create or seed that you're going to create from the cell is actually stable and is repeatable. The reliability of the performance is dependent on the specific memory manufacturer, so sometimes the entropy of an SRAM based buff can be quite poor. There is questionable resistance to side channel attacks because it's sitting inside an SRAM cell. You are seeing currents flowing and therefore it could be actually susceptible to some kind of side channel attack. It is not self-contained IP, i.e. you're using something that's already in the MCU and you're maybe using up SRAM that could be used for some other function. It's got a relatively long setup time because you need to create the helper data to assist the puff. Let's now have a look at second generation quantum driven puffs. This type of puff is available from Quantique. It's an IP block for a standard CMOS process. They call it the QDID or Quantum Driven Identity IP block. It's typically a 64 by 64 array that's baked into the CMOS process of each device, and from that 64 by 64 array a fingerprint is created. The random nature of that fingerprint is based on the atomic positions and the imperfections of the nanostructures in the silicon oxide layer of those CMOS transistors. Basically, the IP measures the quantum tunneling current across that silicon oxide layer. That random nature of that tunneling current provides the ones and zeros of the fingerprint. The QDID measures very tiny currents. We're talking femtoamps. The variations in these currents produce the random numbers which provide a unique chip identity which you can therefore create cryptographic keys from. These second generation PUFs provide the highest possible security. Firstly, they have very high entropy or randomness. This is guaranteed because you're measuring a quantum effect. They have multiple uncorrelated keys within the 64x64 array or within the QDID IP. This means you can generate cryptographic keys on demand and they're uncorrelated to other keys. The identities provided by these seeds are unique, they're immutable and unclonable in this type of PUF. There has been independent testing of the PUF, and we've been shown that it can achieve EAL level 4+. It is also PSA level 2 ready. Of course, these types of PUFs eliminate the need for key injection and all the risks involved with that. The QDID IP has a very small silicon footprint, very low error rates, so there is a very small error correction algorithm, but it's a very small overhead, and we have proven test chips, and these are available today. So let's compare these different root of trust technologies. Let's compare against key injection, SRAM PUFS, first generation PUF, or the QDID, which is a second generation PUF. So do you need an HSM? Obviously you do for key injection. For an SRAM PUF, sometimes you need it because it's limited in the number of keys it can create that are uncorrelated. So you may need to send keys into an SRAM PUF to be wrapped by the PUF. The QDID, of course, doesn't need keys. Keys stored in memory? Yes, they obviously are with a key injection. No, not in an SRAM PUF, because the keys are wrapped using the fingerprint from the SRAM PUF. And no, you don't need to store keys with a QDID. Resistance to attack. The best is the QDID we found, EAL4 certification. The SRAM is good. Key injection, not so much because the keys are held in standard flash. On the cost side, key injection is quite high and high risk as well. Medium for the SRAM PUF and very low for QDID. Entropy is the highest for the QDID, so that's the randomness of the fingerprint or the identity. And quantum computing proof. So the QDID, because it's based on a quantum effect, this is highly immune to quantum computing. Before we close on this presentation, let's quickly have a look at the management of chip-to-cloud security. IoT ecosystems require some kind of management platform to allow the connection of IoT devices to their associated web application. Now, these management systems communicate with the roots of trust which we've been talking about and ensure the security using cryptographic keys and certificates. Quantique's Q architecture includes this type of management platform, and it's called the QuarkLink. This QuarkLink ensures the security of your connected devices throughout its lifetime. To give you some examples of its features, QuarkLink can operate with any root of trust, and it automates certificate issuance, renewal and revocation. It can handle encrypted over-the-air firmware updates, IoT device attestation and authentication, and it actually acts as your IoT ecosystem's certificate authority. Here we show how the QDID and the QuarkLink work together to provide a chip-to-cloud security solution. So here you have the QDID, which would be embedded inside a semiconductor device. The identities of those QDIDs would be extracted and put in a global inventory. This is simply the hash of a public key from one of the seeds inside the QDID, just to give it an identity. There's no secret information extracted from the actual semiconductor device in this case. The QDID would be put on some kind of board, run some software to make a product, a connected product. Once that connected product was up and running, it would try to communicate with its QuarkLink. The QuarkLink would verify that it is a QDID-based device by comparing it with the identity in the global inventory. Once that was done, the QuarkLink would register the device with the cloud service provider that had been configured, and the device could then log into that cloud service provider. During the lifetime of the product, the QuarkLink would manage the certificates of that particular product. This would be involved in renewal of certificates, revoking them, firmware updates, etc. That just leaves me to say thank you very much for watching the presentation. If you want any further information, then please visit our website or email us as shown here on the screen. Thanks again, and you have a great day.